So last time we talked about series and power series. So let's review about the power series first. So a power series is a series of the form A0, A1, x minus c, A2, x minus c squared, and so on. So if you write the sigma notation, n from 0 to infinity, a n x minus c to the power of n. So every entry is a power function. That's why it's called power series. But you have a coefficient, and you also have a variable that's not determined. So you can throw in values in this variable x to get an actual series to compute whether it's convergent or not. And this constant c is called the center of the power series. And the center is always the place where the power series converge. Whenever you put x into c into x, then everything else except the a0 is 0, so always converge. The important thing is, how far can we move our value of x away from c? So if the power series converges and diverges if x minus c is less than r, and if x minus c is bigger than r, then this r is called the radius of convergence. It's literally just the radius, really the radius. So you can go as far as r from the center c in order to make this series convergent. So whenever you have within this radius, you can set your function to be the value of that power series. So the reason why we talk about this radius is, what is the domain of this function? To answer the question, what is the domain of this function? So as long as I take interval from c, so maybe not including the endpoints, because we don't know what happens at the endpoints. As long as I have minus r plus c and r plus c, then I know that this function has a value because the series converge. So I can define a nice function. And sometimes this is the only way we can compute some functions. So we're going to talk about basic functions defined by this power series today. And then we're going to implement, using the Python, how to implement those functions to make a calculator. So any questions from the previous materials? Okay, so I'll give you some list of facts and some definitions. So, but if you are curious about those facts, then I can explain more detail. But I don't want to go through every details because we have a lot of things to do, and this again is just the preliminary material for calculus, the multivariable calculus. So let's start from the exponential function. So sometimes people write it as e to the power of x, but I don't like writing e to the power of x because it seems like it's really taking the multiple x times of the constant e, which is not. So I mean, there's nothing wrong with the notation of e to the power of x, but it feels like you want to understand e to the x as taking e x many times and multiply together to get e to the x. That's not the way we define it. So exponential x is defined to be the limit of the sequence of this form. So here we have x, but x is already given as an input value, so we can consider it just a constant. And what we do is taking a sequence, 1 plus x over n to the power of n, and this sequence is supposed to be always convergent because it's the same way it's convergent for the 1 plus 1 over n to the power of n. It's monotonic increasing, so let's say this is an, then an is monotonic increasing, and bounded above, thus an converges for any x. That's the important part. For any x. So no matter whether x is negative or positive, it's always true. So we can assume that this exponential function is a function from real number to positive real number. So this is the domain. So it's called the domain. I mean, for every function, it's called the domain. And let's say it's the set of all real number, and this is the set of. So this bigger than zero symbol is the subscript, not the same line. It's a subscript, a bar. Just indicate this whole thing is one symbol, the set of all positive real number. Let's try to graph this. Let's try to graph the function. Okay. So let's first define our exponential function. By the way, the exponential functions are implemented nicely in many packages, but we're going to make our own exponential function. So our input is the float number x. And let me check our air conditioner. And then the output is also float value. And, well, so in order to get the value of x, we need large and large n values. And we don't know how large it should be. But what's the clever way of multiplying these large numbers? So basically, whenever you have these powers, you would think that this an is n times of this number, right? 1 plus x over n times and 1 to x over n times. But if I just want n to be very large, very, very large, it's very inefficient to take these much numbers and multiply altogether because we have to loop this much times to get the value. So what would be the clever way of doing a large multiple here? So if I want to take the power of 10, then I have to take 10 of them, or maybe 10 of them, and multiply 10 times, or maybe 9 times. What if I have 1,000? Then I have to take a multiple of 999 times. That's not really helpful, right? But I don't really need a specific number for n. I just need a large n. So the easiest way of doing this is I take n to be some kind of 2 to the power of large integer. But this large n doesn't have to be that large, because if you increase the exponent, the number 2 to the power of n increases exponentially. So when I do that, what I can do is I can simply take the power of 2's many, many times. So actually n times, large n times. So I can just take a powers n times to get 2 to the power as power. So I'm going to do that. So let's take power of 30. So 2 to the power of 30 is quite large, almost a million. So I'm going to, what I'm do is the y is first 1 plus x over, first I need to take n here. Let's say n is 2. I'm not sure whether it has this symbol, but let's try. And y is this, 1 plus x over n. And y is y times y. So I'm replacing y as its square 30 times. So basically I get 1 plus x over n, the original y, to the power of 2 to the 30. So every time I take the square, I get the squares, squaring, and increase the exponent of 2 to the n, and return y. All right, well, let's see whether let's check whether this function works, because I want to check whether this symbol works. And I'll explain what it means. So exponential of, let's see, 1. It's infinite. Well, let's see whether this is correct. Oh, actually it works. Okay, so it works, and y is 30. Why is it infinite? Y times y equals y. Oh, sorry. Okay, so I made a mistake here. So here, I wanted to replace y by y squared. So delete this multiple symbol here. Okay, so let's, yeah, so I get the answer, 2.71828. It's very accurate up to 5 decimal point, because I know that's true by memory. Okay. So what I did in the first line inside of this definition is that I set my number n to be the power of 2 to the power of 30. So what does this mean? It's the shifting operations. So every number or every data in computer is in binary digits. So 1 is basically you have a number which is represented in binary numbers, and so it goes 0 forever. So 1 is just having 1 on the first decimal point, or first binary digit, binary place, and then I move my 1, or actually I'm putting zeros on the right, to shift all the numbers to the left, and then I do it 30 times. So I add 30 zeros on the right side of this one, so 30 times. So then what happens? So okay, so I don't have non-zero value here, so it becomes that it's the number where 31st place is 1 and rest of all the digits are 0. So it's basically it's 2 to the power of 30. Okay, so I get the n equals to 2 to the power of 30 by shifting the digits here. And then I use y to be 1 plus x over n, which is the base of our power. And then I take the squares to get the power of n. So this is legitimate computation because if you have the exponent as an integer or at least a natural number, then by definition, it's just multiplying lots of value, the same values again and again. So we get the exponential. And let's try to graph the graph of this function. Import matplotlib pyplot SPLT, and I'm going to import another package called the numpy as np, and x to be I'm going to use the linspace. I think I mentioned before. So 10 to 10, and then y to be exponential of v for v and x, and then plot x and y. Okay. So I'm drawing my graph from on the interval minus 10 to 10, but whenever you draw the graph, the output is an image. And the image is nothing but a collection of pixels. Image is not a continuous data. Even the screen is not continuous data. You can see, if you come closely to the screen, you can see all the square boxes with a certain color. It's called pixel. So it's all discrete data. It just looks like it's smooth or continuous, but it's not. So if you want to graph something, then you have to connect the finite number of points on the graph and then connect it with lines. And this is how it looks like, because I put minus 10 to 10 with 100 points, equidistanced 100 points, or yes. So you can't distinguish the difference between two consecutive numbers because they are very close to each other. That's why it looks like very smooth, but if you come closer to here, it's not really a smooth point. It's a very discrete collection of pixels. Anyway, you can see a curve, which is the graph of a function, which is increasing. And you can see it's not really increasing when you have a negative values, because it's getting closer and closer to 0. So let's make it a little bit shorter, the interval to be a little bit shorter, and you can see that it's increasing. So whenever you have, on whichever interval you have, you can see the exponential function is an increasing function. So let me write down the properties here. So the property first. So exponential is an increasing function. Which means that if x and y, or maybe x0 and x1 are ordered this way, then x of x0 is less than x of x1. So what other properties do you have? So this is one of the important property, that whenever you have exponential of the sum of two real numbers, what is it? It can multiply two numbers. Yes. So this is true. So I want to change the way of thinking why this is true. For in certain case, you remember this formula from this kind of formula. So it's x1 here, x1 as e to the power of x0 and e to the power of x1. And this is fairly obvious if you have x0 and x1 as an integer. So for example, if you have 1 plus 1, then it's e to the power of 2. It means that you're multiplying e to the 1 2 times, right? So you can split them up. In the same way, you can also split them up when you have a sum of two integers. But these x1, x0 are not integer. It's a real number. So you cannot apply this logic here, right? So this equality, it's not at all obvious. It's not it's not natural. It's very particular. It's very interesting properties and very important one too. So if you want to prove this, you have to go back to the definition of exponential function, and you have to show that the limit of 1 plus x0 plus x1 over n is equals to the limit of 1 plus x0 over n, and limit of 1 plus x1 over n is the same thing. So it's not easy. How would you want to show it? I'm not going to go deeper into this. But anyway. So what other properties do you have here? So you can see from the graph that if you have one value of the exponential function, you can always map a unique value of your x. So which means that you have one-to-one correspondence between the domain and codomain. So exponential is 1 to 1. So domain and codomain are different. It's one-to-one between the real number to the positive real number. Okay. So for any y, so here, for any y inside a positive real number, there exists a unique x in the real number set such that exponential x is equals to y. All right. Okay, so from the third property, if you have one-to-one correspondence, what can you do? Usually you take an inverse function. So what does the inverse function of exponential function is called? What's the name of inverse function of exponential function? What do you get when you invert the graph of exponential function? ln, yes. So, so ln and log are different in the high school curriculum in Korea, but I refuse to use ln. Instead, let's use a log here. So definition, the logarithm denoted as log is the inverse of exponential. So log, because it's inverse, the domain and codomain, the role of domain and codomains are switched. So it's from R positive to R. So now how do you define log then? I mean, how do you compute the log? Well, we define it as an inverse. How do you compute the log? So remember that our final goal is to make a calculator. We need to know the algorithm. We need to be able to compute these the functions. So we define the exponential function and we compute it. So we also have a log function. We need to know how to compute it. So let's say I have log y, and let's call this value as x. And this x is the solution of what? Of equation. What equation? Exponential x equals to y, right? Or it is the root of exponential x minus y, right? So we need to know how to find the root. So this is function in terms of, it's equation in terms of unknown variable x. We don't know what x is. That's the value that we want to get. We know what y is because it's input. So we need to find which x satisfies this equality. In other words, which x makes this left-hand side equals to 0. Then we can find its value, because this x is the value of log. So how would you do it? If you have a graph, or maybe you can just put the ruler on here and then see where that goes, but it's not accurate. You can't guarantee the accuracy here. But let's just use the same idea here. So here's the exponential function. So here is where you have y. I want to know where x is. All I can do is not finding x directly. I can find the range of x, possible range of x, and make that range as small as possible so that there's no difference taking any value in between the range. So x is here, but if I take small, very small, like the radius from x is epsilon. Epsilon usually means it's a small number. And if epsilon, the radius of this range, is small, then it doesn't matter which value I take, as long as the point is inside of this range. So I want to find what this epsilon be. So if I take any value, of course I get the different value, but I know that if I know that this y value is lying on the image of this interval, then I'm okay, because epsilon is small. I get fairly accurate x. So the problem is how to get these interval, or how to get this small epsilon. We're going to introduce a method called bisection method in the following way. So I'm going to just, not writing everything detailed, I'm going to lay out the process in words. So first, let's draw the graph of exponential x minus y. So let's say this is my x-axis. You can call this axis as whatever you want. Let's say z, because I used symbol y already, and y is a constant number here. So when I have, so I want to find where this graph is passing through this x-axis. That's where my z is 0, where this whole thing becomes 0. That's what I want. I want to find, okay, so I want to start from a large interval that possibly contains this root. So let's say I take minus n and n, okay? So this axis is not really at the 0 here, so it's somewhere else here. It doesn't matter. So, and then how do I know that this root is inside of this interval minus n to n? Because this function is increasing function. I know that this root is inside of this interval because if the value of the function is negative on the left end and positive on the right end. So I just increase my n so that this left value and right value have different sign. So once I have that, what I do is taking half of them. So this one, it look like it's in the middle. So let's put minus n here. And take the half somewhere in here. So just half. So this is the first half is actually 0. Okay. And then I compare the sign of three values at the 3 points, here and here and here. So in this case, the sign of the value of the function at the middle point is positive. So I'm going to replace my right end of my new interval with the midpoint here. So in the beginning, I have the interval minus n to plus n, which is a0 and b0. In the next interval, in the next sequence, I have same left end as a1, but now my new right end is going to be b1 here, as 0 here as b1. So I do this with a1 and b1, interval a1 to b1. I also take the midpoint, the midpoint here. It really doesn't matter what the value is. I mean, I keep track of the value of the midpoint, but I'm just giving you the idea here. I'm not going to write down exactly the value of this midpoint. So anyway, so I take the sign, I just compute the value of the function of this function, the exponential x minus y, at that midpoint and see the sign, what's the sign of this value, either positive or negative. And in this picture, it turns out to be negative. That means I'm going to replace this value as a2, and I'm keep the b1 as my new right end of the new interval. So a2, b2 is now here. So you can see that in the beginning, I had big interval. After 2 steps, I decreased my length of interval into quarter of the original length. So first it was this much, that's the first interval. And then second, it was this much. So this was middle, sorry. So it doesn't look like a middle point, but this was middle. And the third one is this one. It's getting smaller and smaller, shorter and shorter. So it's the same thing as I did in the powering. So if I decrease the length of an interval where my root possibly lies on with half each stage, then after 30 steps, it's going to be 1 over 2 to the power of 30 of the original length, and it's very, very small. So after 30 steps, I don't have to carry on anymore because there's no difference between the value of the left end and right end at the point. So let's try to implement this here with the code here. So I'm going to define a log here. So for not to confuse you, I'm gonna put the input variable as y, and I'm going to define my function f to be a lambda function. And this lambda function computes exponential x minus y. So y is already given, okay? And its function f is this function. This function. Okay. So first of all, so make it in order to make it simple, I'm going to start off from minus 10 to 10 interval. It doesn't really matter, but let's say if you want to really make it quite large, and let's make it 10, 1. No, that's too big. Sorry. So yeah, minus 10 to 10 is enough for us now. And then I'm going to set my C to be the midpoint of these points. I'm gonna do it for 30 times. So what I do is keep getting the midpoints of A and B, where A, B will be the left end and right end of my interval every time, and then C will be the midpoint. And okay, so it automatically fills up with this. So if I take the midpoint, yeah, so first I already initialized the value of C as 0, but it's okay to have another definition here. And then I compare the sign of FC. So if FA and FC have different sign, then C, the midpoint, must be the new right end, right? So like this one. So if C, the midpoint, have different sign with FA and FC, so that means one is on below and the other is above, then this must be my new interval. Okay. But if not, if they have the same sign, that means if you take the multiple, then it's positive, bigger than 0. Then in the second stage, you have to change the left end with the midpoint. So A must be replaced by the midpoint. So you're taking half, either left half or right half. So this one is taking, let's say, take the left half, and this one is take the right half, and returning C. So we do it 30 times. So one of the important thing is that we only assume that our value of x must be lying in between minus 10 to 10. So in principle, this law can only compute the value when your input, when the y, the exponential of y is lying between, so yeah, exponential of y lies in between exponential up to the minus 10 to exponential of 10. So it doesn't cover entire value. But that's okay. So let's try to compute some values here. Log maybe 3 and maybe 2. So log 2 is 0.69. I think it's fairly accurate from my understanding. And let's try to graph it. Let's try to graph the graph of the log. So we have, instead of log, exponential, we have log. And we cannot put 0 here. Let's put 1 to 5. So 1 is 0, so maybe 0.1. So there's a hiccup here. So it's when x is 1, I have 0. Let's see. Yeah, so I think it's, so let's make it here. So else if f of elif, f of a, fc is positive, then we get the right half. And else, so almost never happens, but it happened this time. So when it's actually 0, that means our midpoint is actually the solution, the root. So we can just immediately return C in this case. So I'm gonna save this and then run this again so you can see the smooth curve here. So no hiccup anymore. All right, so the graph is just showing that we implemented log correctly, so not a big deal. Let me show you. So this is one way you can implement the log and x exponential. And so before we move on, so is there any questions about this implementation or definitions? So what other basic functions do you have in mind? So exponential log, by the way, why is it enough to have log and exponential? Once you have a log and exponential, you can define any exponential function or any log function you want. So here is the definition. For a bigger than 0, a to the power of x, how do you define it, by the way? How do you define 2 to the power of square root of 2? It's a common question, and I've found that this is very important question, but no textbook is dealing with this question deeply enough to understand the nature of this number. So people usually think that, okay, so this is like 1.4, 2 to the power 1.1, or 2 to the power 1.14. And if you keep doing this, you get some number, and that's the 2 to the power of square root. Well, that actually is, well, the fact is true that if you do this, you get a convergent sequence, but doesn't get you anywhere close to computation, because how would you compute this number? How do you compute this number? So it's 1414 over 1,000. So it's 2 to the 707,500. If you really want to compute this using just arithmetic operations, you need to take first 2 to the power of 707, and then take the 500th root of this number. It's very inconvenient and inefficient. Of course, it's impossible. If you take the 2 to the power of 707, it's very large, so large. And also, you cannot really take the root of 500's power. So, okay. And also, even if you've done that, this number is not anywhere close to the real value of 2 to the power of 2. If you have a small calculator, even any calculator can do this, but no one can do this. Even supercomputer can. Even the high performance computer cannot do this computation. So this is not the way the actual calculator is computing this number. So you can imagine that the a is 2 and x is square root of 2. So how is this defined? It's defined to be x times log 2, log a, and exponential. It's defined as a composite of exponential and log function. It is the definition of this power exponential function. This is called the exponential function with base a. So this is an exponential function with base a. Okay. So we usually distinguish the exponential function exp and the exponential function with the base a. And it's defined by the composition of exponential and log. How about power function? So this is the power function with exponent a. How does this defined? The same way we defined the exponential function. X of a times log x. So because log x is here, the domain of the power function must be always the positive real number. Okay, you cannot throw in negative number. Okay. Doesn't it answer your question whenever you learn first time about the power function, you cannot put the negative number here? I think nobody explained this reason, but this is why, because log function is not defined on the negative number. So let's see. So if you want the log, let's say, so log that we're talking about is natural log, ln, in your high school understanding. If you want to think about common log, I think it's called common log with a base n, a base 10, then you can always just use the natural log and divide it by log of 10, right? So we don't really need different logs. Every log is basically almost same as the one unique log, just natural log here. That's why I don't want to introduce ln or log 10 or other notations. They are just one log. Okay. And also look at this exponential function. So this is this different exponential function than the exp here? So exp is just x. The only difference between this exponential and this exponential is that we have coefficient on top of x. So this log a is just a constant number. It's just a constant. If you can change x to be x of 2x or 3x, whatever you want. It's just the same exponential function, the same way we do here. So notations are different, but it's nothing different than other. It's almost same as exponential function, only differ by the coefficient. So it's not really, we are not talking about totally different function. That's why we only need exponential and log. We can make any other exponential function and log functions. So let's talk about, so we implement these two. Okay. So how about sine functions, trigonometric functions? So we know what sine is, sine and cosine is. So by definition, so it's a definition, by the way. So when you want to start speaking about the terminology, you have to have a starting point. So whenever you want to say about sine function, you have to start with a definition. And definition of sine and cosine is the coordinate of the point lying on the unit circle with the angle theta, where cosine theta is the x-coordinate and sine theta is the y-coordinate of that point. So this angle is measured from the positive x-axis in a counterclockwise direction. So this direction. So you can go the opposite direction, which means that your theta is negative in that case. So we have a nice definition, but the problem is how to compute this cosine and sine. There's no way you can compute it by looking at the geometric picture here. In certain cases, like if you have an angle of 45 degree or 60 degree, you can compute some of them, but not everything can be computed this way. So we have proposition that cosine theta and sine theta, let's use x instead, is computed this way using the power series. So cosine x is the power series 1 minus x squared 2 factorial, x4 4 factorial, and x6 6 factorial, and goes on forever. Goes on forever. And sine function is x minus x cubed 3 factorial, x fifth 5 factorial, and x7 7 factorial, and goes on forever. And what's the radius of this, radius of convergence of these two power series? Actually, it's infinite. Both of them. So it means that the power series converges for all x, for any real number, negative, positive, doesn't matter, any real number. So why is that? Well, first, let's look at the power series first. So you have terms of the power series. On the numerator, you have a powers of x, and the denominator, you have a factorial. Which one you think is increasing faster, powers or factorial? Does factorial increases, power increases faster than factorial? Or factorial increases faster than the powers? Powers? Okay. Anyone think differently? Depends. Yeah. So power is multiplying the same x many, many times, at most n times, right? And the factorial is actually multiplying the factors that you multiply on the factorial is increasing. You have the same amount of number you multiply and the factorial and power. So you have a 7 x's on the numerator and 7 numbers from 1 to 7. But in the factorial, the largest number is increasing, and you have at certain point, the number n will be very, very larger than x. So if you have like x is 1 and n is equals to million, then you have a million factorial dominates, absolutely dominates the 10 to the power of millions, right? So this is decreasing very, very fast. So even you have x large number, eventually you're adding at a certain point almost equal to 0. So, but that's not the proof why the radius of convergence is infinite. Um, um, so look at the radius, so convergence test. So it's just a small review about the convergence test we talked about last time. So look at the cosine, power series of cosine here. So let's consider x is a constant. Let's say x is fixed. And if we take this as a summation symbol, n from 0 to infinity, it is minus 1 to the power of n, and n to the power of 2n divided by 2n factorial. So as I said, let's assume that x is constant. So this whole thing is considered as a sequence that makes our series. And we're going to use the ratio test. And ratio test says, if I have an plus 1 an, which is some number, and depends on the value of L, if it's bigger than 1 or less than 1 or equal to 1, we have different result. If it's bigger than 1, it diverges. The series diverges. If less than 1, its series converges. And if it's equal to 1, we don't know. Okay, so let's try to plug in the formula of an here. So we have minus 1 to the power of n plus 1. It doesn't really matter here. X to the 2n plus 2 divided by 2n plus 2 factorial. So I'm replacing n with n plus 1. So 2n is not become 2n plus 1. It's 2 times n plus 1. And then minus 1 to the power of n, really doesn't matter. X to the power of 2n and 2n factorial. So I can get rid of these, and also this cancels out, and the factorial also cancels out. What happens here is x squared divided by 2n plus 2 and 2n plus 1. So x is constant again, and n is increasing to infinity, so it's 0. So the ratio test says if the limit exists and if it's less than 1, it converges. So it doesn't depend on what value of x is, because it always goes to 0. So this is independent to x. So therefore, I can throw any value to x and the series converge, the power series converge. That's what this r equal infinity means. It's just a symbolic meaning that our power series always converge. So let's try to implement sine and cosine. So we're gonna do a little bit clever way of doing this computation. As I said, we have to, in principle, add infinitely many terms, but it's impossible. So we're gonna add as large terms as possible here. So the definition cosine first, and our input is x, and the type is float, and we're going to return float value. And I'm going to add term, I'm going to define sum and term. So it's going to be, term will be initialized as 1. And I'm going to increase my index from 0 to 30. And basically, I'm going to loop 30 times. Maybe too big. So I'm going to add terms every time. But this term has to be updated. Otherwise, I'm just adding one every time. So after I adding this term, I'm going to update my term to the previous value. To I plus 2 and to I plus 1. So what am I doing here? So it was 1 in the beginning. The term was 1. So I was looking at this term right here. My term is 1. And okay, so I have to be careful whether I have to add or subtract. But and then just look at the absolute sign, absolute part of the terms. So I want to go to the next term, which is x squared divided by 2 factorial. So I need to multiply x squared, and then I have to divide by 2 and 1, right? So this is when I go from this term to this term, that's when I have the index of my for loop, to be 0. So in that case, I need to make up 2 and 1. I have to make my denominator 2 and 1. So here is my 2 and 1. When I equals to 0, it's 2 and 1. So in the next time, the loop is going in the next time, I want to go from here to here. So that's when I have I equals to 1, right? So then what I need is I have to multiply another x squared on the numerator to get x fourth. And then I have to divide 4 and 3 more on top of this denominator to get the 4 factorial. So when I equals to 1, I get 4 and 3 here. So I'm dividing 4 and 3 to get the 4 factorial. So I'm keeping this 2 factorial and divide by 4 and 3 to get to make it into 4 factorial. So now let's be careful about the sign. So every time well, I have to change the sign. So I started from the positive sign. When I moved to the next term, I have to multiply -1. So I get the alternating sign here. So I need minus sign multiplied here. So that's it. So I have to do it for 30 times. And so when this part is over, I iterate again by adding term. And then this term will be added. And then term is updated again. So return sum at the end. So let's print out some value. What would be the nicest value we can think of? So 3.4 over 2. Oh, that's 0. But let's see. Let's check whether that's true. Yeah. So 3.14 is not very accurate pi. So that's why we get not 0. But let's say it's almost close to 0. Yeah. So when I take 3.1415, then I get something to the power of -5, which is almost 0. Okay. getting closer and closer to 0. So I know that this is right. And, well, let's see. Well, how about, well, if I put 0, it's obviously 1. Yeah. Let's define the sign here. Again, sign. So same thing, so almost same thing. So I'm going to copy paste here. So the term is now start from x, not 1. You can see the first term is x. And in this case, the next term is 3 factorial. So I have to divide by 3 and 2. So I need 3 and 2 to here. And let's try out the value of sign here. So if I take, let's say 3.415 divided by 2, pi over 2 basically, then I should get 1. But you can see it's almost 1. Yes. And I know it's true. And it's well implemented. So sine and cosine is here. Of course, it's not completely accurate. It's not accurate as sine and cosine function implemented in the usual package like NumPy. So it has a sine and cosine implemented in NumPy package. If you want to use it, you can just call the name of the function sine in the NumPy package, and let's compare it. So, well, in this case, it's the same thing. So first answer is from our own implementation of sine, and the second answer is from the NumPy package sine. So if you look at the actual implementation, the code of the sine function, you will see that it's a bit different. But in this case, our answer is almost as accurate as the NumPy package sine. Okay, so let's draw the graph. Okay, so we have x is length space, let's say 0.4, 3.14, and I'm going to draw the sine and cosine at the same time. So y1 will be cosine v for v in x, and y2 will be sine v for v in x, and plot x and y1 and plot x and y2. So you can see there's nice picture of 2 graphs. I think the blue one is the first one, cosine. Start from, why is it inverted? I think it's from minus pi. Yes, it's because it's from minus pi. Yes. Okay. Yes. All right. Any questions? It's hot in here, so I'm gonna finish early today. Let's make a calculator. Okay. So we're not going to use any of the function we had in our package. So let's assume that we want to make a calculator after we go. Suppose we go back to the ancient time and with the time machine and try to teach people how to calculate, and we need to make a calculator. Suppose that we have all the manpower and gadgets. We're going to simulate it with the Python code. So what does this calculator do? So basically, if we input some number, it gives some output, right? So we have a certain input type and output type. So we're gonna take an input as a string. So here is the code. So while true means that it goes forever. The loop is forever. And I'm going to, let's say, take the value of input, and then let's print out output. Okay. So when you run this, you see it's going, forever, and it's waiting to get an input after showing this prompt, the symbol here, and then it's waiting for my input. Let's say I have my name, song, and after I get the input, whatever that comes after this string is stored in the variable var, and then I let the print val, so it's printing my same string here. So there's no way I can go out of this program, so I have to interrupt this forcefully, so interrupt this. So let's say I want to make an exit. So if val is exit, then just return it. Oh, it's not return, sorry. Break the loop, okay? So in that case, okay, if I type in anything, I can keep, showing the same string I inputted before, but if I put exit, the string exit, then the program terminates. So it actually exits to go break the loop, the infinite loop. So basically, this is the way I'm thinking about how to make a calculator as a prototype. And all right, so let's change this a bit differently. So I'm going to take an input as an expression, and this expression could be either number or the string of the name of the function. So let's say if I take the input and I will try to make it into a number, or in other words, I'm trying to convert this expression, a string, into a numeric value. So it's just try. So it's just the syntax in the Python that try to convert my expression, which is string, into a float type and store that into value, a val variable here. And sometimes it doesn't work, because if I put Hyosang as a string, it doesn't convert into any of the numbers. So it will fail. So if the value error occurs, that means I typed in a string and not a value here. So if the expression, so in that case, if expression that I try to convert as a value is equal to the string exit, then I'm going to break. That means I need to finish this infinite loop. So for now, let's just try to print out what the expression is, and also the value that is stored here. Okay, so let's see what happens after I've done this. So you're waiting for input. Okay. So when I type in number, doesn't do anything. It doesn't print out anything because there's no value error. So this part is not executed. If the conversion is successful, then this part is not working. But if I put non-value string, then this part is now activated because the value error occurred. It tried to convert my string Hyosang into a value with a float type value. It failed. So it checked whether the expression is exit, and if it's not, it's not exit string. So it prints out the value that is stored before I typed in 1. So value var is 1.0 because I typed it 1 in the previous stage. So the val is stored with the value float 1. And then print out the expression. And then if I put the exit, then it immediately break the loop and finish the program. So now I have to do something with the expression, not just checking whether the expression is exit. I want to see whether the expression is some string that asks us to do a computation. So let me put the code up, maybe just above here. So I'm going to define some value of variable in a dictionary form. So in the dictionary, there's a key and value. So key is literally key, the key, and the value is the content of that key. So when I put the plus symbol, the plus sign will be add, or let me just put a lowercase add. And the minus is sub, and the asterisk is mul, and this will be div here. So here we have dicts. Let's see. Oh. Let's see. I want to have a dictionary of no. Let me go back to our book. They just make confusion here. Oh, sorry. So it's this way. So not dick here. Sorry. Okay. So here I want to make dictionary type, and key and values are defined this way. And you can see I defined the adds. I didn't define what add, sub, mul, and div here. It could be a variable and it could be a function. I will define it these thing as a function. And what is add? Definition of add is taking two value, x and y, float type, and return the float type value by adding these two. Okay. So I keep doing this to find sub and mul and everything else. So I can define using the lambda function, lambda and mul div here. Okay. Doesn't matter whether you use def or lambda to do this. Okay, maybe I think it should go here. Okay, so yeah. So definition of add, sub, mul, div have to come before I use it inside of the dictionary of arithmetic. Here's arithmetic. So just arithmetic operations. And let's go to the program again. So if the expression is exit, I break the loop. But if it's not, then I check whether the expression is one of the four strings here. If this is one of the four strings, then I have to do the operations indicated here. So I'm going to use this code. So I'm going to check all the keys and values, the name and functions in the arithmetic items. And it means that it runs through all the list of key and values. And if the expression is same as one of the name here, what happens? It means that what I input it in the as an expression is either plus symbol, minus symbol, or multiply symbol, or division symbol, then I need another value. I need second value to do the arithmetic operation, right? So I take a new val and then waiting for the input. So input must be numeric value, numeric string, but I don't have any control of user to put the numbers, or it could be a random string. So I just try to get the value that is going to compute the new var to the existing var. So this function is from the content of the arithmetic dictionary here. So if the name are matched, then I use that function, actual function, add, mul, or div, something like that, and then put the value, the old value, and the new value after converting the new value string into a float value, and then compute the value. I tried this, and if it fails because the new var after I put the new var coming from the input is not converted as the function, as a float value type, then in that case, I do nothing because the input is wrong. So I just pass this, right? And then every time I done all this thing, I print out the value, the current value inside of this variable var here. So let me just make it a little bit smaller so you can see every code here. So you can only do the arithmetic operations. Let's try this way. So first I have 1. So when I plug in 1, then it tries to convert it into a float value, and it didn't occur the value error. It prints out the value. And let's try input a plus sign. Oh, sorry, plus sign here. Nothing happens because it goes right into the input part here, this input part. It wants to get the new value. So the second value, actually. So let's say I put 2 here. Then the new var has number 2, and then the conversion is successful. So val is updated as the value of the function with 2 values, the old value and the new value. And the function right now is the content of the plus key, which is the add function. So we add 1 and 2 and get the number 3, and it's printed in the end of this line here. So let's see. 3 is now our new value. I want to, let's say, take a minus of 3, but let's say if I put non-value, like a NA, then what did I do? I wanted to pass. If the value error occurs because of I didn't put the number here, then it just passed, doesn't do anything. There's no update. The value is still 3. And let's try the other thing. So multiplication, let's say multiply with 5, I get 15. Okay. So basically, this is how the calculator works. Like if you have a calculator and you press the button, it's same as the typing in the symbols. And it does the computation and it shows the number on your screen, right? So let's do a little bit. So when you put an exit, it's terminating. So let's do another one. So I want to make a basic function. So basic function. It's also the dictionary. Then I will assign the name of exponential and log. and sine and cosine. Okay. And in the program here, I ran through all the keys in the arithmetic dictionary, and it could be not one of them. So I need, in that case, I need to run through another dictionary, which is basic function, name function in basic function items. If the name matches, then in this case, I don't need new value. So if I have a value and I input the exponential, that means I want to compute the exponential of that value. So just try to compute the value of that function with already stored value here. And there's no way I can get the value error, so I don't have to use the try and except. So just take the value, update the value as the value of that function, and then print the value. So let's run this code. Okay, so let's say 3. 3 is my value, and I want to compute the exponential of 3, so then I get this number. Okay, so if I want to initialize, I just put the number in, then the value will be initialized to that number that I inputted here. So how about cosine? Then cosine 0 is 1, right? So 1.3.1415, the pi. Then how about cosine? Then a minus 1, right? So if I put it wrong, like cosine parenthesis, it's not one of the name I have in my dictionary, so it doesn't do anything. The value stays the same. I mean, it just passes because it doesn't find the same name in the dictionary, so it just pass this command. But you can change it a bit differently. People can make a mistake. So you can make exception. For example, if they make a mistake, like putting this unwanted string, then you can give a warning or modify it so that you read your user's mind and then do the computation correctly. And also you can throw in many other functions. For example, we define the exponential function with the base a, right, or log function with a different base. You can throw in other way of computing the other functions, and so on. You can also make calculator a little bit fancier by taking on user interface. So this one is very primitive. It only uses command lines, and this is not really useful in doing the computation. Sometimes you want to put the entire expression into the command line and then want to compute the exact answer. This one doesn't do that, but it's a very primitive way of doing the calculator. All right, so basically this is the whole code that I have in my book, and also we went through together. Some names could be different, but the core idea are the same. Any questions? Any questions? So this is one of the projects. For the first project, you can choose. There are 9 projects. So every time I'm gonna do 2 lectures and then introduce one project. And the next project is about CAPTCHA. So this one is basically computation with Python without many visual effects. But in the next time, we're going to talk about vectors and matrices. And the CAPTCHA, you see, it's about graphic, right? It's a numeral graphic. And it's fairly easy to make a CAPTCHA, but very powerful to distinguish whether you are robot or human. So we're gonna do that project in the second chapter. So by the way, if you want to go deep, I mean, if you want more detail about the stuff that I mentioned in the class, or detail about the project. For some of them who didn't attend the first lecture, there's a book that I wrote, and I'm just following the book content here. So if you want to buy, if you want to look up more, then you can buy this book. And if you want to see the content before you buy it, you can come to me and after class, and I can show you. All right. So if there's no questions, we'll call it here, and see you next Wednesday.